kids at? Right here, bro. Is anybody taking ACT tomorrow? Folks, we'll be taking a look at London dispersion forces today. 6C14, it's on Google Classroom, 6C14. Intermolecular forces. Intermolecular forces. Folks, here's a great question to ask. A very, very good question to ask. One of my favorite questions. Oh, wrong color, wrong color. One of my favorite questions in an entire Chem 1 year is explaining this. When you can explain this, you understand some things about intermolecular forces. We already used intermolecular forces to explain why water was a liquid at room temperature, carbon dioxide a gas. Do you remember that? You were just kids when we talked about that. You were just little kids. Now you've grown so much. What is it? What question am I asking here? What's the significance of these colors? Red, red, blue, and black. What's the significance? Yes, say that louder. State of matter. When you look at our periodic table, you'll notice fluorine and chlorine are red. Bromine is blue. And on our periodic table, iodine is shown as black. And those reflect the state of matter, with red indicating the substance is a what? A gas. Blue is indicating the substance is a liquid. Black is indicating the substance is a solid. Yet these are all in Roman 7. They are all in the same family. These are Roman 7. This is our halogens right here. And we now have the capacity to explain this. And how great that must feel. I can't imagine how when you came into this classroom just a few weeks ago, since we were distance learning most of the year, and you looked up at a periodic table, and you looked at Roman 7, the halogens, group 17, you probably thought to yourself, why? Why are some gases, another liquid, another solid? Why? We know why there's 2's after these. Why are there 2's after the formulas that I wrote here? They're what? That's how they are in nature. They come in 2's. They are said to be part of the what? They're part of the elements that are found naturally in twos, the diatomic elements. These are found in molecules. The question we're asking is, why is fluorine, chlorine a gas, bromine a liquid, iodine is a solid? Why? Why? Is it because iodine has a stronger dipole-dipole attraction, which holds it together as a solid? Bromine, not as strong dipole. Are these dipole attractions? Do these molecules even have dipoles? How can we tell if a molecule has a net dipole on it? If the molecule is polar, how can we tell? That is part of it. That is part of it. It was mentioned, electronegativity differences. Does that have something to do with the molecules being polar? In other words, having a net dipole, having partial positives, partial negatives? Absolutely. That has something to do with it. Why did we study the valence shell electron pair repulsion theory, VSEPR? What was the point of learning that those little two-dimensional drawings, the little two-dimensional Lewis structures, what was the point of learning to draw the two-dimensional Lewis structures and interpret their shapes? Why do we care how a molecule is shaped three-dimensionally? It's a fair question to ask. Why do we care? What contributes to a molecule having a net dipole? Electronegativity differences. They have to have polar bonds. But what must the polar bonds not do in order for the molecule to have? Say it a little louder. I'm not sure I could hear you. Meaning what? So we've got the central atom. Are you still kind of dealing with electronegativity differences? Why is carbon dioxide, oxygen 3,5, carbon 2,5, difference 1,0? Why is carbon dioxide a gas at room temperature, water a liquid? They both have oxygen on them. They both have polar bonds. We're getting back to why did we spend time on VSEPR? What is a major factor on whether there's a dipole or not? Electronegativity difference is important. A molecule will have a net dipole if and only if what two things are met. This is what we spent most of last week on. I think. Nobody has any idea. We took 6C10 quiz on it. And the last question we answered on 6C10 quiz is the molecule, what is the strongest intermolecular force? How did we get there? Do I have to walk over and open up 6C10 quiz to show you that we spent a week on this? Woo! This is a little embarrassing. Let's take a look at 6C10 quiz. Did you guys spend a lot of time watching those help videos? Yes? Well, who said that? This is a little rough. Maybe we are not ready to talk what I thought we were talking. Has anybody ever seen this before? This is the what? Has anybody seen this before? Have we spent like 2 full days on this? Yes? This one was charged. You remember number 1 here, part 1 was charged, so we came over here and circled ionic. Remember that? We circled ionic. Oh my gosh, what was the next one? This one we circled polar. Do you see right here we circled polar? How do we decide this was polar? Oh, a lot of reasons this molecule is polar. First of all, does it have the same atoms on the sulfur? No, it has chlorines and oxygens, so that was different atoms. Different atoms automatically make it asymmetrical. But there's also a lone pair, and you remember we learned that if there was a lone pair on the central atom, that lone pair does not push the same way that the shared pairs do. Do you remember talking about this? The valence shell electron pair repulsion theory. Those pairs distort the symmetry. Are there lone pairs? Yes. Asymmetrical. Asymmetrical shapes. Then we came out of this box and we had to check the what? Type of bonds. That's where the electronegativity came in. If there are polar bonds, and the molecule is asymmetrical, if those conditions are met, the molecule is polar. It has a net dipole, it has partial positives and partial negatives on it. And they can stick together. We're having to think back all the way to last week to take a look at that. The shape matters. That is why we spent time on the valence shell electron pair repulsion theory. The purpose of spending time on that was so that we could determine, are the intermolecular forces between them strong? Are there dipoles present? Not every molecule is asymmetrical. One of the ones we did on the 6C10 quiz was symmetrical. I think one of them. It might have been 2. I'll have to look back. I know for sure one of them was symmetrical. Which one was it? The first one. You're saying the first one was symmetrical. Yes, it was. The first one was indeed symmetrical. Here we go. However, on this particular instance, it's symmetrical. There were no lone pairs. Did we talk about why there was an arrow pointing from the fluorine to the boron on that molecule? Do you remember talking about that? That is still a covalent bond. It was just a slightly different type of covalent bond, which we called a what? Coordinate, yes, or a dative bond. Tonight we have a video reminding you that we talked about that. Boom! That's negative though. So on this one, the molecule overall has a charge. So it's going to be stronger than a dipole. A dipole only has partial charges. Ionic is a full charge. Then we look down here on this one also had different atoms on it, didn't it? This one also had different atoms on it, making it asymmetrical. There were no lone pairs, but different atoms, it could be asymmetrical. And since there were different atoms and polar bonds, we decided that that molecule was in fact polar. But look at this one. Were there lone pairs on this one? No. Fluorines were trying to form polar bonds, but they canceled each other out. That was a symmetrical molecule. It looks like this shape right here. This shape right here. We had those 4 atoms in the equatorial plane, an atom up and an atom down in the axial plane. It was symmetrical, so the fact that there was polar or bonds trying to be polar didn't even matter, because the only thing you can be when you're symmetrical is a nonpolar molecule. Is a nonpolar molecule. Did you guys actually did you remember talking about this? I'm a little nervous. I'm a little nervous because we get back to this question right here. Fluorine, chlorine, bromine, wrong color, Br2 and I2. Is I2 sticking together as a solid because it has a strong dipole? Or is it sticking together because it's fully charged? The reason we're talking about the intermolecular forces is we've already discussed. We introduced this whole unit by saying they influence what state of matter the object will be. They influence melting points, boiling points, viscosity, solubility, capillary action, all kinds of physical properties. Surface tension, all kinds of physical properties relate to the types of intermolecular forces present. Stronger intermolecular forces produce solids, weaker produce gases. But I get back to the question. What is the intermolecular force between these? Do they have the same types of intermolecular forces between them or different types? Let's draw one. What does fluorine look like? We start with fluorine. There really isn't a central atom since there's only 2 atoms. So I take a fluorine, I'm going to surround it by 8. I will attach the other fluorine and surround it by 8. We're trying to find out, is it symmetrical or asymmetrical? Is the bonds polar or non-polar? You might be like, Mr. Hippenmeyer, you don't even have to draw it because in order for there to be a dipole, you might be saying to yourself, you're wasting your time drawing this, Mr. Hippenmeyer. Why? Because there's only 2 atoms on there. Why draw it? If there's only 2 atoms on there, did I not mention a few minutes ago that there are 2 things that must both be yeses in order for the molecule to have a net dipole? They were asymmetrically shaped, and they were polar bonds. There's no way we can get polar bonds out of the same atom attached to the same atom. Why? Fluorine's 4O. It's attached to another fluorine 4O. 4O minus 4O is what? 0. There is no polar covalent bonds on these molecules. Why draw them? Well, if we draw them, we can also see that it has to be asymmetrically shaped or symmetrically shaped. Fluorine here. Oh, there's one over there. So if that fluorine's pulling this way, that fluorine's pulling this way, they would automatically cancel out, and they would automatically cancel out because they are the same atom. So there are no dipoles on any of these. Chlorine would look the very same. We have 14 electrons to work with. Chlorine's going to be single bonded to the next chlorine, and they also would be surrounded . 2, 4, 6, 8, 10, 12, 14. What would bromine look like? Oh my gosh, it's going to be the same molecule. We have 14 electrons. It's going to be singly bonded. They've satisfied the iodine. They've satisfied the octet rule. Iodine's going to look like this. There are no net dipoles. So there is no partial positives or partial negatives for them to stick together. Yet, gas, liquid, solid, they have the same type of attraction. They have the same type of attraction. Yet they're different states of matter. Why? What conclusion can we make? They are not sticking together. These two are not sticking together. They're sticking together enough to be a liquid. They're sticking enough together to be a solid. They are sticking together. Not sticking together, pretty good, very good. Sticking together, but it's not a dipole that's sticking them together. There's not a partial negative end on one sticking to a partial positive one on the other end. They're not sticking together that way. So what is enabling these to stick together better than those? The fact that the gas, liquid, solid is telling you that there must be an attraction. What is that attraction? Would you conclude there has to be another type of intermolecular force? It's not a dipole. What is the other type of intermolecular force? What is the other type of intermolecular force that's coming into play here? Let's play. You've seen this letters before. Let me show you where you've seen them before. Here's the abbreviation for it. You've seen them before. Actually, we saw these just the other day. Look here, right here. Non-polar molecules. What are these letters right here? L, D, F. Yes, sir. What? Well, let's not talk about size yet until we mention what the force is. LDF is what? London dispersion forces. London dispersion forces is another type of intermolecular force. You see, when you look down here, we already know what ionic forces are. That's when they're fully charged. Electrons have been transferred. We know what makes a polar molecule. We've talked about it. Polar bonds, asymmetrically shaped. Atoms are hugging electrons and becoming partially charged. None of these two are explaining why iodine's a solid, bromine is a liquid, fluorine and chlorine are gases. Because these molecules are nonpolar. They do not have partial positive and partial negative areas. They have something far different. They have another type of force. They have a temporary force. Called a London dispersion force. Take a look. What is the real difference between these atoms? Fluorines, relatively small. Chlorines are a little bit bigger. Bromines are bigger still. Iodines are a lot bigger. There's the pictures of the molecules. What happens here? Well, if there's two iodines sticking together, here's another iodine. Iodine has lots of electrons. How many electrons does iodine have on it? Do you see the atomic number? Iodine's atomic number is 53. So this iodine, every iodine atom there has 53 electrons. Iodine is bigger than fluorine because we know as we go top to bottom what happens to the size. they get larger. True or false? The larger you are, the less tightly you can hold on to your electrons. That's true. Iodine's electronegativity is 2.5, 2.8, 3.0, 4.0. So iodine doesn't pull as hard because it's larger. So its electrons can wander a little bit. In fact, this atom right here, I'm going to outline this one. Right here, I'm going to outline this one in red. This atom's electrons could kind of wander over to this side of the atom. The electrons are in constant motion. The electrons can wander over to one side of the atom. They're not wandering over to the other iodine. They're just moving on this large atom. The electrons are in constant motion. That would make this end of the atom temporarily what? This end of the atom would become temporarily positive. What's it going to do to the electrons on an atom near it? Here's an atom right near it. If this side of that iodine becomes temporary positive because the electrons move over there, then the electrons on this atom might be what? Drawn over to that side. That's called an induced dipole. Induced means it was tricked into happening. We induce a dipole on this atom if those electrons move over. But you're like, okay, we could get an attraction here then. These could attract. But what's going to happen when these electrons move back over to this side? They're in constant motion. What will happen if these electrons move over back to this side? It'll push those away. It'll push those away. Why does iodine become a solid? It is bigger. It has more electrons. It doesn't hold its electrons as well, so they can wander. So if an electron on one of the atoms, the electrons on one of the atoms wander, it'll make it easier to pull electrons near it on a nearby atom. Why? Because they're not held as tightly. Bromine is a little smaller than iodine. It too can have its electrons wander and they can stick together. But now we keep getting smaller. With fluorine's electrons wander as easily. It is small, it is very, very strong. You have a great difficulty inducing dipoles on fluorine atoms because they are pulling their electrons too tightly. So they don't get that opportunity to have little partial positives and partial negatives, or not partial positives, temporary positives and temporary negatives due to the random motion of the electrons. We call these London dispersion forces. Why do they call them dispersion? Because the force can what? It can disperse. Disperse means disappear. Spread out, move around. Disperse the force to other places. It happens with atoms that have lots of electrons that don't hold them as well. They can stick better. I always think of London from the fact that what does the London Bridge do? The London Bridge falls down. What do London forces do? Fall apart, reform. London dispersion forces. Does a dipole disperse? If we have a full dipole on a molecule, for instance, instead of having, here is a chlorine, instead of having another chlorine on there, we have a hydrogen. Hydrogen's 2,1, chlorine's 3,0. There's going to be a dipole going this way, making this partial negative, this partial positive. Does that full dipole, hydrogen bonded to a chlorine, it's asymmetrically shaped, chlorine on one side, hydrogen on the other, and there's a polar bond. We met the two conditions. There's a dipole. Does a dipole disperse? No, it's going to be there. As long as that hydrogen's on the chlorine, it will be there. The hydrogen won't be on the chlorine very long. Why? As long as the hydrogen's on the chlorine, there's a dipole. It won't be there very long. Why? It will kick off the hydrogen as an H plus because HCl is one of our 6 strongest acids. Chlorine is a large atom, hydrogen is a small atom. That single bond is a long bond. Chlorine is stronger. It will rip that electron right off. That bond can snap, leaving hydrogen ion by itself. A London dispersion force can be there and disappear and reform, depending on what electrons are happening on the nearby atoms. The larger the atom is, the stronger the London dispersion force. The larger the atom is, the stronger the London dispersion force. We might break the record for this thing not working the most times in one period. So we're talking about intermolecular forces. In here, we've already talked. This is 6C14. We've already discussed dipole-dipole. Have we discussed hydrogen bonding in here? Yes. But now we are on London dispersion forces. London dispersion forces. What influences the strength of these? It is opposite what influences the strength of a dipole. Are dipoles stronger or weaker on big atoms? Dipoles. On big atoms, they are weaker. Do you remember? Hydrogen on a fluorine and oxygen and a nitrogen is a strong dipole. Fluorine, oxygen, and nitrogen all small, so that dipole is concentrated in a small space. A hydrogen on a chlorine is not hydrogen bonding, even though chlorine and nitrogen are both 3O. Do you remember talking about this? Smaller the atom, the stronger the dipole. The bigger the difference in electronegativities, the stronger the dipole. But with London, they often use a term called polarizability. Polarizability refers to how easy it is to push electrons to one side of the atom or the other. The more electrons the atom has, and the farther those electrons are from the nucleus, the greater polarizability it will have. Large molecules have more London dispersion forces. The more atoms the molecule has, the more places we could get London dispersion forces. True or false? London dispersion forces are found on every atom, on every molecule. Please don't let the everys confuse you, because what do they say when you do true-false questions? When you see every and all, if you're not sure, you should always put what? False. When they make an all-encompassing statement. Everys and alls tend to be falses. But in this case, don't let the every and all. Does every atom on a molecule have some sort of London? Why? The answer was yes. Why? Every atom has electrons. If you have electrons, they can move around creating London. But small atoms, it's very weak. Small atoms, the Londons are very weak. We're going to go ahead and stop right here today. We will pick back up tomorrow with how these forces relate more to the different physical properties Many of you might be taking, some of you may be taking the ACT test. I don't think anybody here in this classroom is taking the ACT test, but we are only going to post one assignment for Tuesday. If you would be taking the ACT test tomorrow, you could do that assignment Wednesday. If you're taking the ACT test on Wednesday, you could do that assignment tomorrow. So whatever assignment is posted for Tuesday will also be for Wednesday. We're not going to add on another assignment to respect those students that are taking the ACT test. What do we have tonight in here to do? 6C13. 6C13 tonight.